What's going on, everybody? Mr. Diamond. Taking a drink of water. And we're going to be doing two problems that I would have done in class on the board if not for the circumstances of the world that we live in right now. So instead, I'm going to have to do them as a video. So what I really would like you to do, and I'm not your mom, I don't actually have power to make sure you do this, but I'd really like it if you attempted these problems by yourself first and just kind of come back to this as you go through if you get stuck and look for a little bit of guidance or just to double check and make sure you're going on the right path. You could just write down these examples and follow along with them, but I would really recommend that you actually attempt these yourself. I'm not going to do them in this space. I learned my lesson from last time. So I'm going to read through the first ones. I'll give you a brief moment to pause it if you want to, and then we'll get on to actually solving them together. As I take a bite of an M&M really quick. Okay, problem 1. Describe the net force acting on the boat. This is a boat. Make sure it's very clear. Boat. On the boat pictured as both a single vector and as components. So we've got our boat here. We're going to pretend that it's in a stream and there are dudes standing on the sides of the river. And if you go to the notes, there is a picture that actually shows this exact situation. Actually, I don't know if I actually ever went by that slide. There might be. If once the slides are up, you'll be able to see the picture that I'm talking about here. And we're going to pretend we've got two guys standing on either sides of the canal. The person on the top part is pulling at 40 newtons at an angle of 45 degrees from the horizontal or from the middle of the stream. And then the person down here is pulling with a strength of 30 newtons at 37 degrees from the middle of the stream. And then we're going to have to take that and try to find the net force as both a single vector and as components. And then question number 2, you're pulling a box along a floor with a rope. The box is 10 kilograms, the rope is 30 degrees above the horizontal, and the coefficient of kinetic friction is 0.30. What is the box's acceleration? So go ahead and pause the video if you would like to attempt these. Again, I really recommend it. You want to try to have as much practice with the stuff as you can, but I don't blame you if life's too busy and you just want to have you at least get talked through the beginning of it. So we're going to start with number 1. I'm going to redraw my boat here. Make it a little bigger. And this was 40 newtons. This is an angle of 45 degrees. This is 37 degrees. This is 30 newtons. Okay, so our first question is the one about the boat, and we want to know what is the sum of the forces. Let me draw my line here so we can not get them confused. Sum of the forces as vector and as components. So what we're going to want to do, I'm going to first assign these. This is going to be blue vector, and this is going to be red vector. So I'm gonna split them apart. And what we probably are going to want to do here is we're going to do something that's really similar to what we did in the last chapter, which is we're just doing vector addition here. We want to split this into its components, and then once we have it into its components, and once we have this one into their components, we can add all the pieces together. So starting with blue vector. How's that blue come across? Yeah, it looks kind of blue in the writing at least. We're going to have 2 components for it. I'm going to use green for the components. We're going to have our x and our y component of this vector. We know this is 40 newtons. To find our x component, we're just going to have to take, we want the adjacent. We have the hypotenuse, that's ka. So it's going to be, just as a reminder, I was going to try to solve it quickly in my head, but I don't want to get ahead of anybody. So we've got cosine theta equals adjacent over hypotenuse. Move hypotenuse over here. So we'll have our x equals our force in the x direction from this is going to be equal to 40 times cosine 45. Plug that in, 40 cosine 45. You get 28.284 newtons-ish. And then technically this is a 45-45-90 triangle, so you can actually make predictions based on that, but I'm going to assume that you didn't notice that because some people might not. So now we're going to also have to do opposite, which is sine theta equals opposite over adjacent. So this was ka. So Fy is equal to 40 times cosine of, or sine of 45. In that case, you will realize it equals the same thing. And then if you do this like this on the test or on a worksheet, you might go, oh, yeah, duh, it's a 45-45-90 triangle. Silly me. Now, the important thing to note, and just to go back and make sure we're double checking, we're going to assume right is positive. We're going to assume up is positive. So both of these are positive values. We have to make sure we don't forget that on the other one. Okay, now we're going to do red vector. Sounds much more ominous for some reason. This one is not a 45-45-90 triangle. I'm going to use purple as my components for this one, just to map those out. This will be my x, this will be my y. To determine the x direction, I want to have the adjacent. I have the hypotenuse, because the hypotenuse is 30 newtons. So this is going to be set up the exact same way. Cosine theta equals adjacent over hypotenuse. That means y is also going to be set up the same way. Sine theta equals opposite over hypotenuse. So the forces in the x direction is therefore going to be equal to 30 cosine 37. Forces in the y direction are going to be equal to 30 sine 37. See, 30 cosine 37. I got 23.959. And it's in the x direction. It's going this way, so we're going to call that a positive. This one's going to be negative because it's going downwards. And I have my answer as negative, again, because it's going downwards, 18.054 newtons. So now we're just going to take these two pieces, all of these pieces that we've got together, and I'm going to switch to purple. I know I use purple for this piece here, but it's blue and red. It just makes sense to use it. Okay, so sum of the forces in the x direction and the sum of the forces in the y direction. So in the x direction, we have positive 28.284 plus positive 23.959. Again, I just want to keep the positive pieces together so I know that it's direction-based, not the other reasons. And then for our y, we've got positive 28.284 plus a negative 18.054. So as components, this will be our answer that we'll get, 28.284. And I'm not holding values, so my answers will be rounded in this case. 23.959. We got 52.243, which is based on my original problem. It looks like, I think I have it as 3 sig figs on my example in the actual notes. So we're going to go to 3 sig figs, 52.2 newtons in the x direction, and then do 28.284 minus 18.054. I'll get 10.23, which is 10.2 newtons in the y direction. So there's our component answers. And then some answer. So if we have our x component going this way, our y component is positive, so it's going to go this way. We want to know our sum of our forces. We get to use our old friend, old pal, Pythagorean theorem. A squared plus b squared equals c squared, so square root of both of those. Square root 52.2 squared plus 10.2 squared. And it's the square root of that, so it'll be 53.187, which is 53.2 newtons. And then we need our angle, so theta equals the inverse tangent of opposite over adjacent. So it'll be 10.2 over 52.2 tangent 10.2 over 52.2. And it'll be 11.0564, which is 11.1 degrees north of east. Oh, box did it correctly. So as a component, it would be 52.2 degrees or newtons in the x direction, 10.2 newtons in the y direction. As the sum of the force is 53.2 total newtons of force that is directed 11.1 degrees north of east. Okay, there was the first example. And I'm going to go ahead and switch to a different page because I don't want to run into that same problem I did on that last worksheet where running out of space seems to really make things a little bit more confusing. So, okay, let me fold this paper up so I can hopefully put it on screen at least a little bit. And we'll hide that, and we'll hide that. All right. So we are pulling a box along a floor with a rope. The box is 10 kilograms. The rope is 30 degrees above the horizontal. And mu k... Wait. Oh, of course I don't actually have an amount of force. Let's go ahead and... well, forgot that from the notes problem. We'll say if you pull with, we'll say 55 newtons of force. Actually, let me double check. I don't want to make up a number and then it'd be impossible. Pausing. I have returned 55 newtons will work for the problem. So glad I double checked that. Okay. Let's go ahead and draw our picture so we can kind of get this awkward piece out of the way. So I've got my ground. I've got my box that is of 10 kilograms. And then I've got my rope, which is directed 30 degrees above the horizontal. And it has a force of 55 newtons. And then we also know that mu of kinetic friction is equal to 0.30. So based on all of this information, let's go ahead and label all of our components. We know it's sitting here. So it's got gravity. We know it's also got the normal force. But notice that our normal force isn't going to be our only thing in the y direction. Because this is at an angle, there's going to be some contribution to pulling forward as well as to pulling upwards. So we're actually going to not have a normal force that's going to be equal to our gravitational force in this one. And then we're going to be pulling forward, which means there's going to have to be friction involved. Our force of friction, or F of F. So let's go ahead and list out what we've got. So force of gravity, we know that. Force of gravity is just equal to m times g. Force of our mass in this case is 10. Force of gravity is negative 9.8. As usual, we've got our negative 98 newtons, which has become a common theme in this one. Let's go ahead and split the next piece that we really know about. Normally we would say, okay, well, we know this is equal to our force of gravity, but it's not in this case. So let's go ahead and take our force of our pull, and let's go ahead and split that into its components. We're going to want to do that before we can solve any of the other pieces. So I'm going to do a blue. I know I used purple up there. I'm going to use a blue, and I'm going to use a red. And this has a total pull of 55 newtons. So in the blue direction, our x component is going to be, I'm hoping you guys have gotten pretty good at figuring this out without needing to have to actually have me solve for the versions of it, but look back at the other one, it's actually going to be set up the same way. We want our adjacent, we have the hypotenuse, so it's going to solve for 55 newtons times cosine of 30. And so that's going to be a forward pulling force of 47.63139721 newtons. Okay. And then in our y direction, we're going to do the same setup, but it's going to be 55 newtons times sine of 30. Because we're looking for the opposite instead of the adjacent. Sine of 30, I got 27.5, nice and round number. So we're actually going to have our red force is going to be directed upwards on our box, and our blue force is going to be directed this way. So when you're actually pulling at an angle, we are actually going to be reducing friction, which means we may not need the full amount of force that we said on our earlier problems. So be careful in just assuming that you're going to be able to use from previous examples. If you watch the video where I worked out kind of some friction examples, you might go, hey, I recognize that 0.3 coefficient. I recognize this 10 kilograms. I think I can just steal information from it. And you could use the force of gravity, but you have to be a little bit careful because now let's actually sum all of our forces together. So some of the forces in the y direction, we've got force of gravity plus normal force plus force of the pull in the y direction. And then in the x direction, we've got force of the pull in the x direction plus the force of friction. So we have to make sure to figure out our normal force, we're going to need to calculate both of these pieces. So we had to have this split apart first. So, okay, in our y direction, we also know that this is going to be equal to 0. Now, why do we know that? Well, we're pulling a box along the floor. We're pulling it forward. It does not mention it's coming off the ground. It does not mention it taking flight. It does not mention it sinking into the floor. It doesn't mention anything like that, which means there must be no motion in the y direction that we care about. So we know gravity is our negative 98. We don't know our normal force. We do know that our y direction force is going to be 27.5 newtons. So that means if we solve for that, our normal force must be 98 minus 27.5, which I get as 70.5 newtons. Now, why did we need that? We needed normal force because we can't calculate friction without how much normal force there is. So normally there would have been, it's a joke, normally there would have been 98 newtons of normal force directed upwards, but because we're also pulling it upwards in addition to pulling it forwards, that upwards pull is reducing how much, by how much the atoms are in contact from the base of this box and the floor, and it's meaning that friction is having less of an effect on the situation. So now we can go ahead and say, okay, well, we know our normal force. Our force of friction, if I do that over here, force of friction is equal to the coefficient of of kinetic friction in this case, times our normal force. So we're just going to take our 0.30, multiply that by our 70.5. And we will get a 21.15 newtons of frictional force. So now we're going to plug this bad boy into our frictional force. Now, of important notes, this is a negative value because it's going to be directed backwards, just like our gravity was negative because it was directed downwards. So sum of our forces in the x direction is going to be equal to the x pull force, which was 47.63139.721, plus the negative, so basically minus, plus negative 21.15 from friction. So put that in our calculator. So minus 21.15. You get 26.48139721 newtons, but the question asks for acceleration. And sum of the forces is equal to mass times acceleration. So we're going to plug this equal to ma. And if we plug this equal to ma, we can divide by mass, which again, mass is 10 in this case. So we actually just have to move our decimal place. So our acceleration is equal to 2.6, I believe we're at 3 sig figs. 2.65 meters per second squared. There you have it. We combined our vector addition. We had to break this vector into its components, use those components to plug into our forces equations from right here. We had to use our friction equation to be able to solve for this piece that we needed right here. And we used the force equals ma because we knew it was moving. We knew there must be some sort of change in that force. It means there must have been some sort of acceleration. And because there was an acceleration, we could calculate that. And that acceleration in this case was a 2.65 meters per second squared. If you have any questions about this problem or the previous problem involving the boat that we did right here, please let me know. Shoot me an email. In the meantime, though, this is Mr. Diamond. I hope you have a good rest of your day. I hope to see you here from you soon. See you, everybody.